Welcome to the Explainer. Today, we're going to crack a classic coding challenge, one that's all about finding these hidden patterns, these very specific sets of numbers that solve a puzzle. It's a fantastic exercise in learning how to think like a computer. So imagine you've got a box full of numbered tiles. Your job is to find every single group of them that adds up to a specific target number. That's really the heart of the puzzle we're tackling today, sifting through all the possibilities to find just the right ones that meet our goal. Okay, let's get specific. The puzzle is officially called Combination Sum 3. And the rules are pretty simple. You need to find a combination of k numbers that add up to a target n. But here are the catches. You can only use the numbers 1 through 9, and, this is important, each number can only be used once. So for example, if you need 3 numbers that sum up to 7, the only possible answer is 1, 2, and 4. And just to make sure we're on the same page, let's look at a couple more cases. If you need 3 numbers that sum up to 9, you actually have 3 different solutions: 1, 2, 6, 1, 3, 5, and 2, 3, 4. But what if I asked you for 4 numbers that add up to 1? Well, that's just impossible. And why? Because the smallest 4 numbers you can even pick, 1, 2, 3, and 4, already add up to 10. That's way over the target already. Now, you might be looking at this and thinking, it's a math problem. But honestly, it's way more helpful to think about it as a search problem. We're not really solving an equation here. We're exploring this huge landscape of possibilities, trying to find the treasure. And that, right there, leads us to the big question. We know we have to check every potential path, but how do you do that systematically? How do we build a strategy that checks everything it needs to, without getting lost or just wandering down dead-end paths forever? It's kind of like trying to navigate a maze made of choices. To build our problem-solving machine, we're going to use this really powerful algorithmic tool called backtracking. It is absolutely perfect for this kind of systematic search. So what even is backtracking? Well, it's this really clever technique that explores all the options by building a solution one step at a time. And the key here is that it's smart. It knows when it's on the wrong track. The moment it figures out a path as a dead end, it backtracks, it retreats, and tries a different option. The whole thing runs on this really simple but incredibly powerful 3-step loop. First, you choose a number. Then you explore. You dive deeper to find the next number, usually by having the process call itself. That's a technique called recursion. And finally, once that path is fully explored, you unchoose. You remove the number you just added so you can go back and try a different path. This choose, explore, unchoose cycle, that's the engine that drives our whole solution. All right, let's actually walk through our first example again. Find free numbers that sum to 7. We start at the very beginning. Our path is empty, we still need a sum of 7, and the very first number we can try is 1. Okay, step 1, we choose the number 1. Our path is now just 1. The sum we still need to find has dropped to 6. And since we can't repeat numbers, the very next number we're allowed to even consider is 2. Next up, we choose 2, so our path becomes 1, 2. The remaining sum we need is now down to 4. And the next number we can try is 3. So from here, we dive deeper and explore. Okay, so from here, we try our options. If we add 3 to our path, our total sum is 6, which isn't our target of 7. So that's a dead end. We backtrack from that choice, and we try the next number, which is 4. And when we add 4 to 1, 2, the sum is exactly 7, and we have 3 numbers. Bingo! That's a perfect match. We've just found a valid solution. 1, 2, 4. But hold on, our search isn't over yet. A good algorithm has to be exhaustive. It has to check everything. We need to go back up our tree of decisions to see if any other paths could have also led to a solution. We have to backtrack. So we unchoose the 4, then we unchoose the 2. This brings us all the way back to the moment where our path was just 1. We already explored the entire branch that started with 1, 2. So now we try the next possible number after 2, which is 3. We then start exploring the path 1, 3, and so on, until every single possibility from this point has been checked. Now, this is what makes backtracking so efficient. It's not just trying everything blindly. It prunes, or cuts off, impossible branches of the search tree really early. We just stop searching if our combination is already full, or if the next number we're thinking about adding is already bigger than the sum we need. Things like that. This pruning saves a massive amount of unnecessary work. Okay, so that was backtracking. Now let's shift gears and look at a completely different blueprint for solving this problem. Instead of exploring paths one by one, what if we could just generate every possible group of numbers right from the start? This second approach uses the power of binary. The difference in philosophy here is really key. Backtracking is a dynamic search. It's like a detective following leads one by one. Binary enumeration, on the other hand, is more like having a list of every single possible suspect from the very beginning and just checking each one against the evidence. So here's the core idea. Just imagine a panel in front of you with 9 light switches, labeled 1 through 9. If a switch is flipped on, we include that number in our set. If it's off, we don't. Simple, right? Any combination of switches represents a totally unique group of our numbers. In computer terms, these on or off switches are just bits, a 1 for on and a 0 for off. And since we have 9 numbers, we can use a 9-bit binary number to represent any combination we can think of. This binary number acts like a mask that tells us exactly which numbers to include in our set. And here's how that works in practice. Take a look at this binary mask. If we read it from right to left, you can see the bits in the 2nd, the 5th, and the 7th positions are all on. They're ones. This binary string maps directly to the number set 2, 5, 7. It's a perfect one-to-one translation. So the actual process is a pretty straightforward brute force check. We just loop through every single possible binary mask, all 512 of them, and for each one, we ask 2 simple questions. First, does this mask have exactly K1s in it? And second, do those numbers add up to our target N? If the answer to both is yes, then we've found another valid solution. So there you have it. We've just explored 2 completely different machines for solving the exact same puzzle. One is this careful, methodical explorer, and the other is a systematic, exhaustive checker. Let's put them side by side for a final review. Okay, let's compare these 2 approaches. Backtracking feels more intuitive, right? It's like how a person would solve a maze, and it's generally much faster when you're only looking for a small number of items. Binary enumeration is a bit more abstract. It's this clever mathematical shortcut. Its performance is fixed because it always checks every single one of the 512 subsets. This makes it a really good fit for problems with a small, fixed set of items, just like our numbers 1 through 9. But ultimately, these techniques aren't just for solving little coding puzzles. The logic behind backtracking and systematic searching, that's what powers everything from your GPS finding the best route to an AI playing a game of chess. It is a fundamental tool for exploring possibilities in a structured way. So the real question is, what problem